Hey, welcome back, ladies and gents. We are taking a look at the last section in Unit E on sampling distributions and estimation. So we've been talking about confidence intervals, and that's going to lead us into talking about hypothesis tests, and a question which comes up, and it needs to come up whenever you're doing a sample is, well, how big should the sample size be? What should be the N? So up until now, of course, it's always been given to you. But if you were to go out and do your own study, you'd have to determine that. So should I sample 50 people or 100 people, or should it be 1,000 people? Like, how do you figure that out? That's the thing. Hey, just as an aside, I want to take you to a site on election polls. So I'm just going to go in here and type in the poll tracker and for Canada. Poll tracker for Canada. And CBC actually has a great poll tracker. So let's go to that particular site there. And this is updated pretty well daily. So this was last updated, I guess, weekly. So November 17th, 2020. And so there's always these polls going on as to, well, who would you vote for if there was an election today? And so this is what they've got down here, is that 36% of the people would vote for the Liberals, and 31% would vote Conservatives, 18% for NDP, and so on like that. What they show down here is the point estimate with the margin of error. So this is saying here then that the estimate, if we were to have an election called today, then they're expecting that the Liberals would take somewhere between 120 and 212 seats. And their best guess is 171. That's over on the left-hand side there. And the Conservatives is 108 is their best guess, and it's somewhere between 79 and 142. That is the point estimate with the margin of error. And it's quite large right now because there's always a lot of people which are undecided. And especially when we're far away from an election, there's a lot of undecided people. So that's why you've got a large margin of error. If you think of the election in the States, which just happened on November the 3rd, it was hard to call a lot of states. It actually took several days in order to call states. But they're using that whole concept about what the margin of error is. And when the margin of error is small enough that a particular lead in one party is greater than the other, give or take the margin of error, and there's no overlap, then they tend to call it. And so in this particular case, we would tend to look at this and say, well, the Conservatives are not overlapping that line which you would need for a majority in the government. And the margin of error for the Liberals actually does have this, that includes the majority line here. And so there's a pretty good chance that they would win an election. There's a 48% chance that they would win. Now, notice though that there is an overlap of the lowest that they have for the Liberals, which is 120, and the highest they have for the Conservatives, which is 142. So you've actually got quite a large margin of error. And that is why it's only a 48% probability that the Liberals are going to win a majority. One thing I'm not going to get into is because we're dealing with a number of different parties, it's a little more complex than just a straight binomial problem. So we're not asking, would you vote for the Liberals or not? This is a little more complex kind of distribution here where you're taking into account a lot of different parties here. And so that's why the margin of errors are different here. But it's the same concept. So let's get back to what we're looking at here. And that is, well, how do you determine the size of the sample? By the way, most of the samples that they have that determine those election poll results there are usually around 1,000 or so. And that'll give you about a 2 or 3% margin of error, 3 to 4% margin of error. And we'll see that in a few minutes here. But let's take a look at how this thing works here. It all comes down to what's the acceptable margin of error. And so when you're talking to a decision maker, so if this is, you're doing this for your own company, of course you are the decision maker. But if you're doing a study for somebody else, then you would ask them, well, how accurate do your results need to be? So for instance, you might be interested in, well, what percentage of people will buy my product? And suppose we find that the answer when we do a survey is, 25% of the people will buy the product. And that is accurate with about a 10% margin of error. So that would be anywhere from 15% to 35%. Is that okay, or is that too large for you? And by the way, that is based on about 100 people. And so they might look at that and say, no, I'd like it to be smaller than that. So you say, okay, well, what size would it need to be there? And so you say, well, maybe within 5%. So that would be anywhere from, say, 20% to 30%, right? And so that'd be a 5% margin of error. So you look at that and you say, okay, a 5% margin of error means that we would need to sample 400 people. Again, you're going to see that when we go through this today. Listen here. Can you afford that? Do we have the time for that? Can we gather that from 400 people? So that's the kind of thing. There are, incidentally, a lot more sophisticated ways. So in stats, we talk about things called type 1 and type 2 errors, and then a cost-benefit analysis based on the probabilities of type 1 and type 2 errors. You have a thing called the power of the test, which is looking at the costs associated with type 2 errors and so on. And that's stuff which we haven't got to, and we'll probably talk more about that in the next stats course. So there are more sophisticated methods, but a good place to start is just to have that conversation with somebody and say, well, how accurate do you need to be? Like plus or minus 5%, 10%, does it need to be 2%? And that actually will be the strongest determinant in terms of what your sample size is. So let's take a look at how this works. If you take a look at a confidence interval, the endpoints for a confidence interval, as we saw before, are found by taking a point estimate, x bar, plus or minus a margin of error. And so the margin of error is this guy here. And let's give that a symbol. Let's call that E. So E is equal to Z alpha over 2 times sigma over the root of n. And again, that could be a T statistic with an S, and you could have an FPC factor tacked on to that. But the generic formula that we have, or the simplest formula that we have, is just the E is equal to Z alpha over 2 times sigma over the root of n. So that came from confidence intervals. Now, let's solve for n. If you solve for n, this is what you end up with. And the thing to note is that all of those parts there are known except this guy, right? So you would determine the level of confidence. And typically for business problems, you would have, say, a 95% level of confidence, so you know that that Z alpha over 2 value is going to be 1.96. The margin of error, that's the discussion that you had with the decision maker, or you could go through a more complex procedure to figure out what the acceptable margin of error is. So you might say, well, within 5%. But what about the sigma squared? The problem with the sigma squared is that that is a population standard deviation, right? Sigma squared is population variance. And the whole point of taking a sample is that we typically don't have access to the whole population, so maybe we don't know that. So what do you do in that case? Well, there's 4 things that you can do in terms of putting in a value for that sigma squared. One is to use a hypothesized value. So This will make sense in the next unit a lot more. So if you have a hypothesized value of what sigma is, then you would use that. The second thing here is to use a sample standard deviation from a previous sample of the same or similar units. So if a study was done before, let's say it was a past study that was done, then you would use that particular standard deviation. That would be a sample standard deviation that you would use. Or if you're, say, doing this for red deer, and you could look at a comparable city, maybe Lethbridge or something like that, and use, maybe they did a study, and so you could use the standard deviation that they had, because those are comparable. Here's a really important one here, and that is to conduct a pilot study, which you should always be doing when you're conducting a sample anyways. So a pilot study is where you just run the survey past a small number of people. They recommend about 10% of the population, but it can be much smaller than that. So when you guys are doing this in 307, you'll actually be working on a real project, and I'll say, run the survey by about 10 of your friends and relatives or people that would be part of the target population. And it just helps you to determine whether your questions are good, whether there's any ambiguity to the questions, whether they have any problems filling it out, all that kind of stuff. So it's really important to run a pilot survey. But from that, you can actually then do some simple calculations and come up then with an S that you can stick in there. So that it'd be an S squared. The fourth one is use your best guess, and that's not recommended. It really isn't. It says if either the first two are used. That's actually a typo there. It should be if either a 2 or 3 are used. And that's because I actually went in later and added number 1, which is really important here. So if you're using a sample, then of course you would be using an S, and therefore you should be using a T distribution instead of a Z distribution. Okay? All right, let's take a look then when we're talking proportions. So for proportions, it's the same kind of animal here. So you've got, from our confidence interval for P, we've got this. P bar is equal to plus or minus a margin of error. Let's call that margin of error E. Let's solve for N, and that would give us this formula here. By the way, this formula, the formulas in this particular section are on your formula sheet at the end of your manual, and that's something that you'll bring into your last exam. Now, it says here, P can be estimated using any of the 3, actually 4 methods. Again, I made that change and didn't see that change there listed before. So back here again, you can use a hypothesized P, or you can use a sample P from a previous sample study, or you can do a pilot study and use a P bar from that. Or you can make your best guess, which is never a good idea. But there's one other thing that you can do here, and that is when we're talking about confidence interval here for a proportion, the most conservative value that you can put in here is a P of 0.5. All right, I want to show you where that comes from. And here's the thing, guys and gals, is you don't need to remember this next part, because I'm going to jump into calculus. I love calculus. I took a whole bunch of courses in calculus. And a lot of you are taking calculus right now. So I'm just going to take an aside here. You don't need to remember this derivation here. But what I would like to do is to take the derivative of n with respect to p bar. So these guys are just constants, and so really it's this part that we're talking about here. And so that's going to be equal to the derivative of p bar minus p bar squared. And the derivative of that turns out to be minus 2p bar plus 1. If we set the first derivative equal to 0, that will give us a p bar equal to 0.5. We know that that is a that this is a maximum because the second derivative is negative. And so we know that that's a maximum possible value there. Another way to take a look at that is that if you just take a look at this part in here, which is p bar times 1 minus p bar, try out a couple of values. So p bar of 0.5 times 1 minus p bar will give you 0.25. If you make this 0.4 times 0.6, that would give you 0.24. See, that's smaller. 0.3 times 0.7 would give you 0.21, and so on. Anything other than 0.5 gives you a smaller calculation here. And so the most conservative value that you can choose here is a p bar of 0.5. So what that means is that if you're looking for determining the sample size and you're not given any of these other things up here, if you're not told a p bar from a pilot study or from a past sample or a hypothesized value, then just simply use 0.5. And don't confuse that with 0.5, which is your alpha. It's a different animal. This is talking about a p bar value. Okay, so 0.5 then is what you can use if you're not given any of the others. One other thing we need to take a look at, and oh, by the way, again, remember, you don't need to know the calculus there. That's just an aside, which I think is just really a cool thing, and some of you will find that interesting. One other thing that we need to take a look at is that, well, what if you're talking about a small finite population? In other words, you know what capital N is. And it's not really big. We're not talking 20 million adult Canadians, right? We're talking about some of the problems that we looked at before, 200 RDC instructors or 500 bicycles, that sort of thing. And so your little n, your big N is fairly small. In that particular case then, what you do is you calculate your N using this formula here, this formula or this formula, depending on whether you're looking for a proportion or whether you're looking for a mean. And then you do an adjustment. So this is an adjusted N. We'll call it N prime. And it's equal to this here. So this is found first, and then you stick it in, right? And you get an adjustment. Let's walk through a problem here. We'll actually do two problems here, and I'll leave the rest for homework. How many persons would be needed? So that's a dead giveaway that we're talking about what is N. Okay, so what is N is what we're asking about. How many persons would be needed? We need to sample with 95% accuracy. So that gives us then, we're talking about a confidence interval of 95% for the average from you. Within half an inch, the within half an inch is your E. Okay, so half an inch, 0.5. Assume that the population standard deviation is 3. So that was given to us, or we could have done a sample or a pilot or something like that, right? So formula is going to be equal to N is equal to Z alpha over 2 squared times sigma squared over E squared. We've got everything we need here except for the Z alpha over 2. We're talking about a Z 0.025, right? 95%. We know that number. It's one of those famous stats numbers. It's 1.96. Again, I'm going to assume that you know that, how to do that. Otherwise, go back into some of the previous videos and take a look at how that's done. So let's plug in what we've got. 1.96 squared times 3 squared times 0.5 squared. And that comes to, what do we get here? 138.3, whoops. 138.30. And so what we would do is we would round that up to 139. So you would have to sample at least 139 people in order to end up with a margin of error of ½ inch. Now what we're going to do is we're going to go down here and say, consider the problem above. Suppose there's 270 female business students in the program. Is that what we were looking at? Yeah, college females. So that's your N, your big N. How should the sample size be adjusted to reflect this? So this is where we use this formula from up here. N prime is equal to N, little n times big N over big N plus little n minus 1. So what you want to use here is not the 139 rounded value, but use the original 138.30. So take it to a couple of decimal places, 138.30 times 270 over 270 plus 138.30 minus 1. And that comes to 91.68, which we would round to 92. Now, practically, you would probably take that to 100, but what we're saying is that because this is a fairly small population here, you don't have to sample 139 people. You can sample only 92 people in order to get an error of 0.5. So that's the answer. That's how many people you would need to estimate or sample. That leaves us with one last page here. So I'd like you to do this for homework. How many students would need to be sampled with 95% accuracy in order to determine within 10% the proportion of students at RDC? Notice that all you're given here is the level of confidence and the error. So you're not given the p-bar. So again, what do you do in that case? And then we're going to make an adjustment here. 5,000 students at RDC. It's actually bigger than that, but we're just going to use something like that. And then there's one more problem down here that I'd like you to do. That takes us to the end of this long but important unit. Remember, always do the additional problems at the end. So there's a good couple of pages here of problems to work through. Most of them are confidence intervals. The last few here are ones where you're dealing with the N. So how many, right? How large a sample, and so on like that. Okay? The rest are confidence intervals. And here's the answers down here. So the confidence intervals, and then the last ones here are calculating the sample size. So that brings us to the end of this particular unit.